Yes, children, now let us see in the case of boron. Ve2 I am leaving because you can understand this part now. Since boron 2p is there, I want to discuss that, okay? So 1s and 2s, you know how the bonding and anti-bonding molecular orbitals are arranged. Now come to p. P is a set of 6 orbitals, 3 here and 3 here. 2 boron atoms are combining, right? Now when 6 atomic orbitals combine, 6 molecular orbitals will be formed. Now these 6, you know very well that they are of the form px, py and pz. Same way you have px, py and pz of the other boron, right? Now px and px will combine to give you 2 orbitals, one bonding and one anti-bonding. Same way py and py will give you one bonding and one anti-bonding. PZ and PZ will give you one bonding and one anti-bonding. Now how these 6 molecular orbitals, how they are arranged, you see. Now initially at the lowermost end, energy corresponding to this, you have pi 2px, pi 2py. Now why pi? I told you pz with pz is sigma, right? So px and py, they will form only pi bonds. So their overlap is above and below the plane, right? So you have the molecular orbitals with least energy is 2 pi 2px and pi 2py. Now pi 2px is bonding, uski corresponding anti-bonding pi star 2px is here. Same way pi 2py is here, pi star 2py is here. Okay. Now this pi 2px and pi 2py, they are associated with the lowermost energy, and sigma 2pz is having slightly higher than this. Now you may ask, sigma is much more stable, so this should be associated with lower energy. How is it that it is above? That is because, now just imagine this sigma 2pz, had it been here and these 2 pi, if it was in this position, then what happens is this 2pz, if it was down, there will be repulsion from the anti-bonding 2s and the sigma 2pz, because the energy level will be close to each other. And this repulsion, what it has done, it has pushed the sigma 2pz up. And this pi 2px and pi 2py, they are having different orientation. So they will not be repelled by the electrons of the anti-bonding 2s. Okay, that is why pi 2px and pi 2py are here, and then sigma, because the repulsion has pushed the sigma 2pz up, right? And then इसकी corresponding anti-bonding होगी और इसका जो anti-bonding है वो ऊपर है. Now total number of electrons are only 2, is it not? It's having 1s2, 2s2, 2p1. So that one electron, total of 2 electrons are there, they will be accommodated 1 each. Why? Because they are of same energy. According to Hund's rule, what do you say? Electrons are filled in orbitals of equivalent energy when they are first singly filled, and then availability of electron के हिसाब से वो उसकी pairing होगी. Now electron अब है ही नहीं, 2 electron में खत्म हो गया, ठीक है? Now the rest of them are all vacant. Okay, so when you write the molecular orbital configuration for this boron, it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and then you have pi 2px1 equal to pi 2py1. Equal to क्यों है? Because they are same energy level orbitals. Okay, molecular orbitals. And then you will find out the bond order. That is equal to 1. And presence of unpaired electron in this pi 2px and pi 2py makes the species paramagnetic. That is why B2 is paramagnetic. Bond order is 1. Okay, it is paramagnetic. Now you come to nitrogen. Now carbon, you can do it yourself. Okay, you can try. Nitrogen is having 3 electrons each. So a total of 6 electrons are there, right? Now these 6 electrons, how they are accommodated? See, first you will put 1 in each and then pair it up. So 6 में से 4 हो गया. And the rest 2 will go to sigma 2pz, right? And all these anti-bonding levels will be free. Nothing will be there. Because according to energy level, Aufbau principle, what does it say? the electrons are filled in the increasing order of energy levels. So this is having the lowermost energy, तो इसमें fill किया, फिर उसके बाद ये fill किया, इसमें भरने के लिए है ही नहीं आपके पास electrons, right? So when you want to write the molecular orbital configuration, you will write it like this: sigma 2px2 equal to sigma 2py2, then sigma 2pz2. That's it. Vacant वाला यहाँ पे लिखने की जरूरत नहीं है, जहां तक filled है वहां पे stop कर दो. So bond order will be half of 10 minus 4. 10 कैसे? 2, 2 plus 2 4, 4 plus 2 6, 6 plus 2 8, 8 plus 2 10, and 2 plus 2 4. So 10 minus 4 is equal to 3. So bond order is 3. And here again there is no unpaired electron. So nitrogen will be diamagnetic. मैंने N2, ये C2 नहीं है, N2. N2 is diamagnetic, right? Now, when you come to elements beyond nitrogen, that is oxygen, fluorine and neon, if you see, there is a small change. What is the change? You were having till nitrogen, this pi 2px and pi 2py, they were down, and the sigma 2pz was up. Now there is slight interchange in position. Sigma 2pz will be down and these two will be up. Why? Because now in the energy level diagram, if you see the anti-bonding 2s level and sigma 2pz के बीच में काफी ज़्यादा difference है. So repulsions are not that significant. That is why sigma 2pz can be here and then pi 2px and pi 2py. Is that clear? Till nitrogen, the energy level difference between this sigma 2pz and anti-bonding 2s, it was very close and it pushed the sigma 2pz up. But from oxygen onwards, this problem is not there. So sigma 2pz is down and pi 2px and pi 2py are having higher energy. Is that clear? Now total of 4 electrons are there in the case of oxygen. So 4 plus 4, 8. 8 में से पहले 2 डाल दिया, बचा 6. फिर इसमें एक एक डाला, फिर pairing की, तो total of 6 are over out of 8. Now 2 more are left and these 2 will go as 1 in each. Actually I have shown for neon here. You just try to understand. Now in the pi star 2px and pi star 2py, there will be 1 electron each in the case of oxygen, right? This is for neon what I have shown. For oxygen it will be 1 in each, right? Because of which oxygen will be paramagnetic in nature. Okay, so this is your molecular orbital diagram and these are molecular orbital configurations. Okay, now you can directly write the configuration using sigma 1s को छोड़ के k लिख करके आप इसको सीधा लिख सकते हो इस तरीके से. And then you can find out what is the bond order and whether there is any unpaired electron or not. That will be easily visible to you even in this molecular orbital configuration. There is no problem. Unless you are asked to draw molecular orbital diagram, you need not have to draw. Otherwise, you can write the configuration and show all the properties. Bond order क्या है, paramagnetic character, diamagnetic character, everything you can show. Right? So for oxygen it is 2 and for fluorine it is 1 and for neon it is 0. That means neon does not exist in the diatomic state. Right? So that is about your molecular orbital theory. Now dear children, I have given you many questions before and this one question let me again tell you. O2, O2 minus, O2 positive and O2, 2 minus. Now look at the number of electrons, 16, 17, 15, 18. Is it not? O2 में 16 है, O2 minus में 17 है, O2 positive में 1 कम और O2 2 minus में 2 ज़्यादा. ठीक है? Now what is going to change is only in this region, right? So you have from oxygen it is 2pz first and then pi 2px, pi 2py. यहाँ तक तो कोई प्रॉब्लम नहीं है. ठीक है? 16 इलेक्ट्रॉन्स हो गए. Then you have pi star में एक एक है, O2 में अभी अभी देखा हमने. ठीक है? Now O2 minus में कितने इलेक्ट्रॉन्स है? 17 है. तो 17 है तो ये पाई स्टार 2px में एक और इलेक्ट्रॉन ऐड हो जाएगा, इसमें एक ही रहेगा. देन O2 प्लस में दो में से एक नहीं होंगे, तो पाई स्टार 2px में 1, इसमें 0. देन 2 माइनस में दोनों में 2. इस तरीके से बॉन्ड ऑर्डर निकालोगे. यू विल फाइंड दैट 2, 1.5, 2.5, 1. You can't blindly write the values by mucking it up. You are supposed to show the configuration and then only write the bond order. Okay, you cannot write it just like that. And based on that, you can say O2 positive is the most stable. Greater the bond order, greater the stability. So decreasing order of stability you can find out by finding out the bond order, right? So this is about your molecular orbital configuration. Like I can ask you, say for example nitrogen or oxygen में से nitrogen to become N2 positive and O2 to become O2 positive. I have given you these questions. Just go through the questions that I have given you before. Out of these two ionizations, which is more favorable? So you find out the bond order of N2 plus and N2. If this is greater, that means this ionization is favorable. And if this is smaller, then that ionization is not favorable. Is that clear? So that way you have to find out.